Hi everyone. In this video, I'm going to correct a material point kinematics exercise that will review position, velocity, and acceleration vectors, starting from two equations of motion along the x and y axes, which are in inches and expressed as a function of time in seconds. The first question consists of deducing the equation of the trajectory of the material point M and its nature from the given equations x of t equals 2t plus 5 and y of t equals t squared plus 5t plus 3. In the second question, we will express the vector OM. Then comes the third question to determine the velocity and its magnitude. The same work is required in the fourth question to determine the acceleration and its magnitude. Finally, the last question involves an interesting parameter, the radius of curvature of the trajectory at the initial time t equals 0. Let's begin the correction now. To find the equation of the trajectory of moving point M, we express the time t in the equation for x of t and substitute it into the expression for y of t. As you can see, we obtain y of t equal to x squared minus 13 divided by 4. This is indeed the equation of a parabola. There you have it. It would be helpful to represent the trajectory with a parabolic branch on the xy plane and identify the starting point at time t equals 0. Let's move on to the vector OM, which is obviously the x-coordinate of t along the y-coordinate and the y-coordinate of t along the j-coordinate. Thus, we find OM equals 2t plus 5 I plus t superscript 2 plus 5t plus 3 j. This vector is variable, as you can see, and depends on the time factor. Two examples of the vector OM are displayed at the bottom of the screen for two close times, t equals 0 and t equals 0.5 seconds, with a graphical representation on the xy plane. It is easy to deduce that this vector evolves in an increasing manner as a function of time. Here we need to be more careful, as we need to determine two parameters, the velocity vector and its magnitude. The expression for velocity is always obtained by differentiating the position vector with respect to time. Therefore, in our case, after differentiation, v becomes t equals 2I plus 2t plus 5 j. From there, we can easily calculate the magnitude of the velocity by applying the formula for the square root of the sum of the squares of two velocity components. After calculation, we will have square of 4t squared plus 10t plus 29. Don't be surprised when I tell you right now that the acceleration is also easy to calculate, since it is also obtained by differentiating the expression for velocity with respect to time. Thus, we differentiate the components of the velocity we just found. After calculation, we will see that the acceleration is independent of the time factor and is equal to twice the vector j. Finally, its magnitude will be 2 inches per second squared. Every type of trajectory necessarily has a radius of curvature, ρ, at each point along its path. This radius can be calculated using the formula, ρ equals v cubed divided by the magnitude of the vector v cross a. In our case, we will calculate the radius of curvature at time t equals 0. As you can see, this radius varies with time. The further we go, the larger the radius becomes. Finally, at t equals 0, the radius is its smallest value, which is equal to 39.04 inches. At the end of the exercise, I invite you to a quiz.